Okay, so I want you to go back. Make sure you're with me here, guys. Yeah, it's important. When you go to page 3, you have this graph here. Okay, like at the bottom of page 3, you have this. And if you followed my notes, it will look like this, like it's filled in, right? What I need you to add, do you remember I told you in the video, if you watched it, that these functions do not touch the x-axis ever. They do not cross it. There's no x-intercept. And that is called the asymptote. So if you could please write that down. I will put in brackets horizontal. I would say this box is probably a really good one to have on your study sheet. Like whatever's in this box is a very good summary. It doesn't have everything, right? But for exponential functions, this box I would most definitely. So asymptote is the word we use, right, to denote some sort of, it's like an imaginary line that no graph will ever touch, right? So this exponential curve here will never touch the x-axis. Therefore, there's what we call a horizontal asymptote here. Okay, so both scenarios have that, so it never ever crosses. So if I ever give you a bunch of points and there's an x-intercept, okay, you know for sure that it's not an exponential function. You know for sure, like if there's a point and you realize there's an x-intercept, it cannot be exponential. So it's kind of like to rule it out. That's a good way to rule it out, that most definitely. Okay, let's go to 7 as I mentioned. Let's do the word problem. So I need you to have that asymptote. I need you to have heard it. I don't know if it shows up, but now you know. Exponentials and logarithmic functions are the only ones that have that term mentioned, asymptote, because it doesn't touch. Okay, so for word problems, okay, remember we've got our exponential, and by exponential I mean that the exponent is always going to be x, okay? A and B cannot be negative in this course, so we do not explore those, so you don't have to worry about that. But here it is. That letter A here is often referred to as the initial amount that we have, and exponential is often dealing with population, right? Or it will also talk about radiation sometimes, or bacteria or whatever. So it's the initial amount that is given to you by that number that's going to be in place of A there, okay? And then B is what is happening to the initial amount. Okay, so that number that's right next to the exponent tells us what's happening to the initial amount. If B is greater than 1, it means that you will start with A and then it will just keep increasing. If B is less than 1, it just means it's going to be decreasing. Okay, and X will often be time. Okay, so there's your 3 components. Those are the only 3 components you ever need to worry about. Okay, I will make a note here. Are you following? You're following us, right? Sometimes you have different letters. So you could have the population over time is equal to, let's say there's 500 flies in this little box, okay? And we will say that you will have something like this. You could have something that looks like that, T over 2, let's say. This may look scary, but don't worry about it. You'll just put the exponent in as you see it here, and I usually put brackets in there. So right? This is the exponent still. And just make sure you put it in brackets like this when you enter it into your calculator. So sometimes the exponent kind of looks scary, but don't worry about it. You just type it in as is, and the calculator will do the rest for you. Okay. All right. You should always ask, is the population increasing or decreasing? Is the investment, is it growing, or are you losing money? Okay. To determine B, read the question. It will be less than or greater than 1. Okay. So if the question mentions that there's a decrease of 5%, okay, if there's mention of a decrease of 5%, the equation would be like this. Okay. First of all, we will go 1 minus 0.05, because that's 5%. Okay. And you're left with 95%. So B is 0.95 in this case. So an example of the equation that would result from this context would be y is equal to, I'm just going to use A here, okay, because I don't want to put a number, but you would have 0.95 to the power of x. And I don't know if you look at this, it should tell you that you're losing 5% every time, because you're left with 95%, right? If you have 0.95 in there, that means that every year that goes by, you'll only be left with 95% of what you had before. Okay, so when it says decrease of 5%, a lot of students just want to put. So I'll say error. Right, common error would be y is equal to a 0.05 to the x. This is wrong. Okay, this is whenever there's a decrease, you need to first take that away from 1, and then you come up with the value of b. This is b right here. B is 0.95. Okay. Alternatively, if the question mentions an increase of 5%, the equation would be, first of all, you say you're increasing from what you had before. Okay, so you think of the initial as 100%. So that means that you're going to be left with 1.05. Okay, so B in this case is 1.05. So an example of an equation would be y is equal to a times 1.05 to the power of x. Okay, so it's always with respect to 1. Okay. I can't tell you how many times I've had a question on the exam where it says, it gives you an equation, it's like the population is increasing at a rate of 105%, 5%, right? They give you some options, and you should see this and saying, oh, the rate is 5%. I'm always going up by 5% compared to 100, right? So there we go. So let's write some equations based on what we've just learned here. Write the following equations that would model each scenario. You invest $6,500. This is your A. This is the initial amount. Okay. Your investment, right? You earn 2.5% annually. Sorry, the per is supposed to be gone there. It's just supposed to say earn 2.5 annually. That means per year. This is indicating growth, right? Growth of 2.5%. Okay. Therefore, B is going to be 1 plus 0.025. I always turn that into a decimal, right? So B is 1.025. That's what B is. And now I can come up with my equation. Y, which is the amount of money you have after a certain time has passed, will be 6,500 times 1.025 to the power of x. Okay. And here x is time in years. Y is amount of money after a certain time has passed. So you can tell this is increasing just by looking at this value right here because it's bigger than 1. And this is how much I have to invest in the beginning. Okay? We're going to do more investing stuff once we get to finance. A small town with a population of 578 B's, sorry, I typo there, C's, that's that, right? This is B's, please change that. So a small town with a population of doesn't make sense. It is C's. A small town with a population of 578 sees a decrease of 12.5% in its population each year. Okay, so it's seeing a decrease. So the town hall is meeting and they're like, hey, we're decreasing by 12.5% every year. Okay, so A is going to be 578. Okay, I'm going to do it slightly differently here. B is what? Well, it's always with respect to 1. And since we're decreasing, we're going to subtract that percentage from 1. Okay. So there you get B is 0.875. So you have both components that are necessary here. So the population that this town will have, if it starts with 578, you'll have 8.75 in here as B to the power of x. Okay. Where y is population and x is time in this case years. Because time can change. It could be minutes, it could be hours. It depends on the scenario. Okay. All right. The number of bacteria in a petri dish is 25,000. Okay. So this is bacteria in a petri dish. This is A. And it triples every hour. Okay. What does that mean? Yeah, you got to go y is equal to 25,000. And you literally just go, you put the 3 in there. This is B. When it says triples, you put that in there. Just like that. B is equal to 3. And to the power of x. Where y is the number of bacteria and x is the time in hours. Okay. If it's a doubled, it doubles every hour, then you would put a 2 in there. Triples, doubles, that's the most commonly used scenarios. Okay. All right, continue. So this is just to understand how I put them together. How do we put them together? Okay. How do we set it up using exponential? I'm just going to mention it briefly. When you see the letter E, Euler's number is denoted by the letter E. It is an important constant. If you're going to go into engineering or anything like that, you're going to deal with E a lot. Okay? But what you need to remember is that E is 2.71828 and so forth. I don't need you to remember it because our calculator has E. Watch right here. If you look up, on top of the division symbol, there's an E right there. So you can just go second press that, and then hit equals, and it will tell you what it is. Or, look up here one more time, this ln button has an e to the power of x. So you could just go second ln, and then you can actually put an exponent onto the e. We just want exponent of 1. Hit enter, you still get 2.718. Sorry, you can't see that. The exponent of 1, and then you still get that. Okay, so this is what you need to remember, that e is actually a number. It's like pi. Do you ask questions about pi ever? Can I have a piece of pie maybe? But that's about it, right? But pi, we all know, is 3.14156, and it just keeps going, right? Same thing here. It's a constant that is used in population growth and things like that. Do not confuse Euler's number with Euler's constant. Euler's constant is this, so just make sure you don't have that on your study sheet, because it's not going to be an issue. You're not going to have to worry about this at all. Okay, so from now on, if you see E, you know what we're talking about. It's that it's a constant. Sorry, it's actually a number that we use, and we can access it on our calculator. So if you ever see this, you should not be scared. You know that that, right, is 2.718, and that just keeps going. And that's going to be a growth scenario, right? Because b is bigger than 1, it's going to increase like this. All right. The next two terms before we start talking about, we actually tackle a word problem, because that's where I really want to get to, a word problem. Doubling period, very important, folks. Highlight this, have that on your study sheet. Doubling periods and half-life. Those are the two that are very, very prevalent in this particular chapter. When you hear doubling period, we are in exponential function territory. No questions about that. Exponential or logarithmic, you will see that as we get along. For example, the amount of time for money or population to double. Okay, that's what that means. That's a definition of doubling time. So I'll give you an example. Let's write down the example so you have a concrete example. A certain bacteria of 1,000, okay, doubles every 2 hours, let's say. This is what they use, like, right, to determine, like, if you could keep track of, like, bacteria, viruses in your body, and what makes you feel sicker is like that growth, right? Like how fast do the bacteria or virus, how fast does it grow? So what you need to make is that little T-chart, right, where you compare time and population. And make sure you get this part right. This is what a lot of folks miss. A certain bacteria of 1,000, that means that in the very beginning, it's time 0, and you have 1,000 bacteria at the very beginning. And so when it says every 2 hours this population doubles, it means that you have to add 2 hours to your time, and you end up with 2 hours here. And what will happen to your population? It tells us that we're doubling our population. So from 1,000, we're now going to be at 2,000 after 2 hours. Another 2 hours go by. We're now at 4, correct? What's going to happen to my population? It's going to be 4,000, and so forth. So you will be able to put this into L1 and this into L2, and off you go. You make your exponential function out of that. What if, example, 1,000 bacteria doubles every, let's say, 5 hours? you have another bacteria that you're studying and it's in the lab and it says every 5 hours, that's the doubling time, you would do the same thing. At time 0, you have 1,000. It says 5 hours, correct? So after 5 hours, your population will double. Another 5 hours go by. So you'll be what, time of 10, correct? You double your population one more time to get you to 4,000. So you just have to be very careful that the doubling is happening to the population, not to the time. Let's say one more time, the doubling is happening to the population, not to the time. A lot of students double both. By the way, 0 times 2 is 0, right? So if you times it here, you shouldn't get the correct answer. Okay, and then again, we would put this into L1 and this into L2, and then we can actually make our own equation by performing our quadratic cubic exponential regression. Sorry about that. Half-life is the time it takes for a population to reduce to half of the initial population. This would be applying to a decreasing function. Let's highlight that part, that doubling time, you're increasing the population. Obviously, it's always doubling. When it's half-life, you're actually doing the exact opposite. Your population is getting to half of what it used to be. In several cases, instead of decreasing the function, the question will talk about decay or a decrease. It means the same thing. So let's say example, okay. A bacteria population of, let's say, 10,000. It has a half-life of, let's say, 15 minutes. You should immediately recognize, oh, half-life, that means the time it takes for my population to go down to half of what it used to be. Okay, that's what it means. So here again, time and population. It could be time and money, right? So it would be apply the same. It still says that at the beginning you have 10,000. After 15 minutes, so we're talking minutes here, right? 15 minutes go by. What's my population going to be there? Half of it, that's going to be 5,000. Okay. Another 15 minutes go by. So you're now 30 minutes, right, from the very beginning. You'll slice it in half one more time. So it's 2,500. L1, L2, and we're going to find the regression. Okay. You're going to find the regression. I think, can we do this regression here? I didn't do the first one. We don't have a lot of space, but stat, calc, and we're now going to use exponential regression. Okay, we're going to use that function. So let's enter this into our L1 and L2. I'll invite you to all do that. And go stat edit 0, 15, 30. Stat, calculate, and you got to find exponential regression. It's hidden. It's not even on your main screen. You got to keep scrolling down until you find exponential regression, which is option number 0. You select that, and then you go second 1, comma, second 2, alpha trace. Oh, I didn't put a comma down. Alpha trace, enter. And there's our exponential function. And I tend to go 4 decimals. You'd be just fine going 2 decimals. But what does this tell us? When this is less than 1, we know it's a decreasing function, right? Which is what we're expecting, because half-life means you're going down in your population, you're reducing it by half. How much is it going down by, roughly? Let's just go like that. If this is 0.95, it means that it's going down by 5%, right? 0.05, which is 5%, every minute. Because right now we're dealing in minutes, so that's what you would go with there. So we'll just leave it there for now. Let's do a word problem together. I just want to say this, like you should have on your study sheet exponential logarithmic section. Doubling time and half time is exponential. Like you don't even need to wonder, oh, is this cubic? What is this? We're in exponential territory, okay? So that is very unique to exponential functions. Doubling time and half-life. All right. The population of a certain species of bees is modeled by the equation, as you can tell. And I want to make you aware that the province is going to have just a big unit that is just called functions. So all functions that you will have learned will be present, and they'll mix it up on you, like the functions. So you should be able to right away tell, oh, my exponent is x, right? This is an exponential function for sure. And I'm told that p is the number of bees, right? That's that. And t is the number of years. Okay, so we know that it's every single point on this is time, because time is on the right side, and bees or population is my y variable. Okay, immediately you know that. So let's answer. What is the initial population? It is 1,500 bees. Okay, explain. I know this because the exponential function y is equal to a bx, like that, right? Tells us that a represents the initial amount. That would be good enough right there. So you're telling me that you understand this is an exponential function and it normally looks like that, and a represents the initial, and you also clearly stated that it is 1,500, so full marks there. Is the population increasing or decreasing? Increasing, yeah. I will circle increasing, and I will explain because b is greater than 1, we have an increasing function. Okay. That's it. That would all that I need in this case. And you've already told me that you understand what b is. Okay. If you want to be very sure, I would go I would just say b is equal to 1.15. And then I know for sure you understand which value is b. Okay. What is the rate of increase or decrease? We already know that it's increase, right? What is the rate of increase? Stated as a percentage. And so you just go b, I already know what it is. I'll just go 115 minus 1, I'm left with 15, which is the same thing as saying 15%. So the population is increasing at 15% per what? This is where you have to be careful. The time here is in years, correct? So that's going to tell us what to put here. I will connect them in a bit. If this had been time in minutes, we're observing bacteria in a petri dish, you would say 15% per minute. Okay? So you have to just match whatever your time is here. That's amazing. Okay, so far we've just like taken apart the equation. We've been able to answer without even typing this into our calculator, just by looking at it. Okay. D, how long will it take for the bee population to double? You're trying to figure out the doubling time. You don't know what the doubling time is. You want to figure it out. Okay. So how would you go about this? I want you to first type this into your calculator, this equation right here. Remember, we're entering our equation manually, so go ahead and turn off plot 1. You don't want that on at all. And then we're just typing this in. 1500, 1.15, use your brackets, right? And here's the kicker, this is very important. You got to go exponent, right? Exponent, and then type x. Okay. And I already know that my y-intercept is 0, 1500. So my y max, I'm going to go to my window before I even graph it. And I'm going to change my y max to, I don't know, 2000. I have a little bit of negative everywhere for the mins. Y max, I'm going to go 2000. I'm going to graph it. So I see some of it. I'm going to chase the curve a little bit. I'm going to go Y max even higher. I'm going to, let's say 5,000. And you're just going to have a feel for it. Like I can't tell you what the magic number is here. But there is your exponential curve. Okay? So watch this, folks. When you want doubling time, you say this, initial population is 1500, correct? You want to double this. You want to say, how long would it take to double the initial population? So you're wondering, right? If you have 3,000 bees, right? How long would that take? So you let y2 equal to 3,000 bees. Because remember, bees is my y variable. And you're going to find out how long it takes to get from 1,500 to 3,000, which is the doubling time. So go to your y equals, let y2 equal to 3,000. And you may have to adjust your window. Okay. There it is. Okay. It's where it crosses here. It's a little tight, but I think it'll work. Second trace 5. Enter, enter, enter. And it was able to find it. So second trace intersect. And I get that time is 4.96 years. In this case, years. Let's explain what you just found. This is the doubling time. Population will double every 4.96 years. That's what you just found. Every 4.96 years from now on, will tell you that you're doubling your previous population. Okay, so if you want to know how long will it take to get to 6,000, well, it takes another 4.96 years. Once you're at 6,000, what is double of 6,000? 12,000, right? Well, it would take you another 4.96 years. So this is your doubling time right here, and you find it just by doubling your initial amount, letting that be y2, and then go find that intersection. Okay. So this is very specific doubling time. How long will it take for the population to reach 9,250? Right? I will let y2 equal 9,250. Then go second trace, intersect. Let's go ahead and do that. And I'm going to have a problem with my window. I know that already. That's a very high line, right? Like you won't even see that on my screen. So I'm going to go to my window and change my Y max to 10,000 or so. And there it is. I still have a problem. Chase the curve to the right. So I'm going to go X max, right? Go to your window. What should I make X max? I'm going to try 100. It's overkill, but it shows me the intersection, so I'm fine with it. Second trace 5. Just hit enter 3 times. Because you only have 2 curves, they only cross each other once. So there it is, 13.02 years. That's how long it will take the population to get to 9,250. How many bees after 60 months? So let's say they're asking you for time in months. Okay. Convert 2 years. You have to make sure your time is right. So 60 divided by 12, that's 5 years. If this had been a decimal, you use the decimal, right? Because everything in our equation is based on years. How many bees after this many years? So they're basically saying, if time is 5 years, what is your population? So we're going to go second, trace, value, x is equal to 5. Second trace 1, x is equal to 5. 3017.04. Can you answer that way? No. I'm going to write down the whole thing. So you just round it at that point. 3017 or 3018 bees. No problem. Gee, if the maximum capacity of a beehive is 15,000 bees, okay, determine the domain and range. So I'm boxing it in. I'm saying no more than 15,000 bees can be there. So make a little sketch here. You're going to start here, and at some point when the population reaches 15,000, you're going to stop. The beehive can no longer support more bees. What's this point right here? That's 1,500, right? 1,500. So you need to have your start, and you need to have your stop. I know that my population there is 15,000. I just need to figure out how long did it take to get to 15,000. What will I do again? Y2 is 15,000. Second trace, intersect. And again, everything you know about functions and how to find points is the same. It's just that exponentials behave a little differently. That's all. So my Y max is a problem again. I'm going to change my Y max to 18,000 or something. Try it again. Okay, so now I'm going to change my Y2 to 15,000. And it's crossing right there. I'm going to find the intersection. And it's 16.48 if you round that. don't be scared to go decimals with your domain and range. Some of you are going round numbers. Let me rewrite this. 16.48. Okay. So what is my domain going to be? Domain, we're talking time. From time 0 till 16.48. Okay. You're closing it. You're closing it. What's my range? The lowest amount of bees in this particular model is 1500, right? That's my initial. And I go as high as 15,000. So in this case, everything is closed in, no round brackets anywhere. And I'll do the graph, and then you could do some of your own. Try it yourselves. You need to try it to get comfortable with this. Graphing, let's go to 10. You already have a bunch of points that are going to help you. So arrowheads on the axes, label them. This will be time in years. Some of you did not put the units down, right? This is population. And just to be sure, we're going to go population. That's the number of bees. And in this particular case, I want to go all the way up to 15,000. Okay, so 5, 10, 15, that works just fine. So maybe I'll just go up by 5,000 at a time. Okay, 5,000 at a time there. And out here, I need to make it all the way to 16.48. So 5, 10, 15, 20. That's good enough there. I'll just go a little past, just make it nice. Okay. And so 1500, this is 2500, so 1, 2, 3, 4. Oh, every box is worth 1,000. So 1500 should be right there. That's one of my points. The other one is the end, right? 16.48 is right about here. And I'm going to go all the way to 15,000 right there. And I would say it's tough to do this, in my opinion, right there. It's tough to, like, what, does it go straight to it? Does it do this? Like, what's happening? Can I ask you to at least find one more point in between somewhere? You're like, what do you mean? You go second trace value, right? Second trace value, sorry. And let x be anything you want. Anything in this area here. I'm going to choose 10. Okay? Let x be 10 and then find out what a good y value is for that particular point. So I put that in my calculator, second trace value, x is equal to 10. I get 6,068.34. After that, the province doesn't have a case anymore. Like, if you have it close enough, it's good enough. So 10, 6,000 is right just over the 6,000 mark. And now you have a pretty good reference here. So you go and just connect it to that one. And then you connect it to that one. So try to make it arc a little bit. No arrowhead stops here. I tell my students, make sure your graph matches your domain and range. Did you hear that part? Make sure your graph matches your domain and range. If you have it closed off, this should not have an arrowhead continuing into infinity and beyond, right? It should stop. So let's put it that way. I just have, so this is just an additional point. For reference, okay? I don't know how picky they're, like every year it changes a little bit. Like some years they've been picky when students just went straight to the point. Like you need to have a bit of a curve to it. That's what the shape is all about. Okay. One last note, and then I need you to work a few yourselves. If there was no restriction on the max population, write this down, okay? Then my graph would have looked something like this. 0, 1500. This is just a sketch, okay? This is not really a graph. It would just go like this, and that's what the graph would look like if there's no indication of a stop somehow. But quite often they do put a limit. They say, hey, you can't have more than this. Okay, for money, for example, would you want a stop on the amount of money you have in the bank account? Ideally, you just keep growing, right? Just keep growing forever. However, if they say, hey, you retire at 65, you take it all out, then there would be a stop to it, right? So just read carefully. What would the domain and range have been if there had been no stop? Domain is my time. So it'd go from 0 to infinity, right? And range? What's the lowest? 1500, that's right. All the way to positive infinity. Okay, so this is this is an aside, but you're not used to infinities in word problems, but exponential and logarithmic functions do have exponentials as part of that scenario. Okay, I'll let you, so either you update your study sheet with the charts and pages 3, 4, do a word problem or two. I will also draw your attention to this part right here, the domain and range of a non-contextual scenario. On pages 4 and 5, I graphed a bunch. Okay. And this is on page 5. The domain, if it's not a word problem, both ends just keep going indefinitely, like it just keeps on going from negative infinity to positive infinity. That's why the domain is this. What about the range? Do you notice something different about the range? There's no equal, okay? Y is greater than 0 because it never touches the x-axis. So that is new. I would definitely have this on my study sheet too, the properties of an exponential function, so you get that right if there's ever a multiple choice question or something like that regarding that case. Okay, I'm going to post the answer keys. I have them ready to go. It goes from 12 to 19, and I know it's a lot. I don't think I would expect you to do all of them, even though I would love it if you did. I think I said I have the ones that I really would like you to do. Hold on. Yeah, 12, 14, and 17 has, no, 18. 18 has doubling time. 18 has a doubling time scenario. So you need to be able to draw from that. All right, I'll pause it here.